Alright, we're talking about estimating a population proportion. So there was an activity before this, and let's say I had a bunch of chips in a bag, red chips and blue chips, and you take a sample of 50 and you get 27 red chips, and your goal is to try to estimate the proportion of red chips. So we can figure out p hat, the proportion of red chips in this bag, by doing 27 over 50 and get 0.54. So, well, how can I use that information to figure out what the value of p is? So if you think back to chapter 7 with our sampling distribution, we know that the shape is approximately normal as long as n times p and n times 1 minus p are at least 10. We know that the center of that sampling distribution is at p, and we know the standard deviation is p times 1 minus p over n, provided that this population is at least 10 times the sample. When we do these confidence interval problems, we're going to want to make sure that we want to make sure that we have met are random, normal, and independence. So random, so when I go back and look at this problem of here, it is random. It says it's a simple random sample. Normal. So last chapter we would check n times p and n times 1 minus p. This chapter, remember, we don't know what p is. If we knew it, we wouldn't be trying to estimate it. So since we don't know what p is, we think that p hat will be a good replacement. So we're going to plug p hat in for n. So again, back up here, p hat was 27 divided by 50, or 0.54. So n times p hat is 27. N times 1 minus p hat is 23. Both of those are greater than 10, so the sampling distribution is normal. For the independence check, so since I sampled without replacement, so they took a bag, or they took a sample of 50 chips, they didn't take one chip, put it back, take another chip, put it back, take another chip, put it back, and so on until they got 50. They just took a handful of 50. So that's sampling without replacement. Since you're sampling without replacement, you are violating that independent condition because you're actually changing the probability each time you take out, when you take out that big sample and don't put it back in. Since we're violating that condition of independence, the standard deviation formula might get a little bit thrown off. So we're going to check this condition here. So as long as the sample is less than 1/10 of the population. So yes, we're going to say that there's at least 500 chips in my population. Alright, when we create a confidence interval, so yesterday we talked about you would take the statistic plus or minus the critical value times the standard deviation of the statistic. So the statistic is p hat. The critical value we're going to talk about in a second, and the standard deviation. So this was the formula that we had back in chapter 7. But we don't know what p is, so we're replacing it with p hat because we think that that's a good replacement. When we do that, replace that with p hat, that's actually called the standard error. So it's the standard error of the sample proportion. So basically the standard error is when we have the standard deviation, even if it's estimated from date, so it's estimated by plugging in that sample statistic, then we call that the standard error. Alright, so then that piece that we're missing here is just this critical value piece. So we have this as p hat, we have this right here that we're using for our standard deviation, so we just need our critical value piece. Alright, when we're finding our critical value, if our normal condition is met, we can use a normal curve. So we can use like our familiar normal CDF or inverse norm. Yesterday when we were talking about using the spicy chicken, we had 68, 95, 99.7. We said this was 1, this was 2, this was 3. Now we were using 2 for 95, but we could really use the table or use the calculator using inverse norm. We could get the more accurate value. Instead of 2, we would use 1.96. So if you think about it here, remember our inverse norm, we have the area to the left, comma the mean, comma the standard deviation. I'm using the standard normal distribution. That critical value, which is going to be represented by z star, is going to come from the standard normal. It's just going to tell me how many standard deviations away I want to be. So about 95% here in the middle. So I have 0.025 in each tail. So 0.025, so if I do inverse norm 0.025, I get negative 1.96. If I did inverse norm 0.975, I get positive. I'm just going to take the absolute value and use 1.96. because back up here, that formula already has a plus or minus in it, so I don't need to repeat that plus or minus. So there's the 1.96. Finding the other ones, so you can see that here. There's the 99% one, there's the 90% one, and there's the 80% one. Now, you should be able to find any different percentage. 95% is going to be the most commonly used. So now you have all the pieces. Now remember, this piece after the plus or minus is your margin of error. So when we write it like this, it just kind of helps us see what the margin of error is there. Alright, when we do these types of problems, we're going to start using this 4-step process here. So when we do these problems, these 4 steps will be state, so what parameter do we want to estimate at which level? The plan, we're going to identify the method, we're going to check our conditions, so random, normal, and independent. So today you're doing a 1-sample z-interval for proportions. Random, is it collected randomly from an experiment that was conducted randomly? Is the sampling distribution normal? So you're going to check that. Independent, are the observations independent? If not, is the 10% condition satisfied? If the conditions are met, we're going to do the calculations, we'll show our work, and then we're going to do an interpretation, which we talked about yesterday. So here's the example. So the first step is to state what I'm doing, so I'm going to find a 95% confidence interval for the true proportion. The second step, and note here, it just says construct and interpret, so it doesn't actually tell me that I need to follow the 4 steps, but whenever you see that, you need to follow the 4 steps. If you don't follow the 4 steps, it can make the difference of you getting like a 4 on an AP question versus getting a 1. So second step, I have a 1-sample z-interval for proportions. Is it random? Yes, it says it was a random sample. Normal, so I'm going to check that condition. Both of those are greater than 10, so yes. Is it independent? Yes, there's at least 1,240 couples. Alright, I'm going to plug everything into my formula. Remember, this piece is the margin of error. I'm doing 95%, so that 1.96 is that critical value. Found that back on page 2. You can write your interval like this, and so I'm 95% confident that the interval 0.586 to 0.752 captures the true proportion of all couples who tilt their heads to the right when kissing. And those are the problems. Only this one right here requires you to use all the 4 steps. This one breaks it down for you. And that's it.